Assalamu alaikum and good day everyone. I am Shahina Salim Jumani here in Science Lab to provide resource to secondary school teachers. I hope you have heard much on permanent magnetism. Here I am to demonstrate and explain the temporary magnet. Pause the slide and go through the objectives. Take a pause and think or go through your reading materials and SLOs. In National Curriculum of Pakistan's Grade 4 to 8, go to the SLOs which are learned in previous sessions such as recognize the difference between a magnet and a magnetic material and recognize that the freely moving magnet comes to resting point in a north-south direction. Now coming to our topic, SLO S06B48 compare different types of magnets and how does temporary magnet works. For advanced concepts, once students are done with this chapter, you may move to the next experiment as mentioned in slide or of your choice. So, what is magnetism? Uh-huh. Well done! Magnetism is a force that makes certain materials pull away or push away from each other because of the way tiny particles are arranged. You can ask your students, why does an ordinary iron nail, when touches the paper clips, behave exactly like a non-magnetic object, even though it is made of the same material as many magnets? Take a pause, think. Do not forget to like, share and subscribe our channel. Leave your comments below and we'll respond to you. Let's dig into the experiment to find out. The story begins in a school laboratory where readily available equipment such as a box of paper clips, bar magnet, and iron nail are present on shelves. In here, a simple iron nail sits on a table, unremarkable and silent. Nearby lies a strong bar magnet and a small pile of paper clips. At first glance, nothing suggests that these ordinary objects can reveal one of the most intriguing microscopic behaviors of matter. Yet, this small setup becomes a window into the phenomena of magnetic induction. Educators, do remember when your listeners see it, they are more likely to retain it. And when they are fully engaged in performing the experiment with fun and enjoyment, chances are higher of remembering it. I understand. I'm not pushing you to change the assessment and exam patterns at the very moment, but the impact with these small activities a great educator can create is lifelong. Now we will perform step by step procedure. Let's hear and do as I instruct, or you may pause the video and give your learners time to perform and reflect. The experiment starts with the learner picking up the iron nail and lowering it toward the paper clip. The nail refuses to lift even a single clip. Why? Why is that so? Well, iron has tiny magnetic parts that point in different directions, so they cancel each other and the nail shows no magnetism. The nail behaves like any piece of metal with no visible magnetic strength. Sounds interesting? Hold on, let's carry on with next step. The learner then brings the strong bar magnet close to the same nail. As the north pole of magnet touches the head of the iron nail, something invisible yet profound begins to unfold. Within the nail, the magnetic domains start to align. Some enlarges as they absorb neighboring domains, while others rotate slightly until they face the same direction as the external magnetic field. This reorganization is what physicists describe as magnetic induction. Remember this terminology. Through this process, the iron nail becomes a temporary magnet. Let's have a more closer look. Have you wondered why this happened? If the nail becomes a magnet when touching the bar magnet, why does the magnetism disappear after we remove the bar magnet? Shouldn't the magnet stay a magnet? Let's understand this concept through schematic representation. Imagine a series of small arrows inside the material. Before magnetization, randomly arranged domains, no net field. While during magnetization, you can see the arrows upwards. Domains are aligned, producing net magnetism. And after magnet is removed, let's say iron, the domains are relaxed and magnetism is lost. The core concept here is the magnetic field surrounding the strong magnet can temporarily magnetize objects made of iron, nickel, or cobalt. When this happens, it is said that the object is magnetized by induction and that the object is temporary magnet. When the north pole of the magnet touches the nail head, this becomes the south pole and the nail point becomes the north pole. The particles, dipoles, of the nail are lined up in one direction and the whole nail becomes temporarily a magnet. As soon as the permanent magnet is taken away, the particles revert back to their random distribution and the nail's magnetism disappears. So here there are key learning points which are induction, the process through which a magnetic material becomes temporarily magnetized due to the influence of a nearby magnetic field. Polarity, when the north pole of the magnet touches one end of the iron nail, that end becomes the south pole and the opposite end becomes a north pole. Another, temporary versus permanent magnetism. Iron is easily magnetized and demagnetized, while materials like steel retain magnetism longer due to the internal structural resistance. Nickel, used in magnetic alloys and coatings, cobalt retains magnetism were often found in permanent magnets. Non-magnetic materials such as copper or aluminium cannot be magnetized by induction because they lack the necessary domains. So here the core concept we do not want to forget is when a magnetic field from a permanent magnet acts the material on such as iron, it induces magnetism by aligning the magnetic domains, tiny magnetic regions within the material. This induced magnetism is temporary. Once the external field is removed, thermal motion randomizes these and the magnetism disappears. I hope you have learned these concepts. Now please give your students some time for the post-assessment. Here are some questions. For example, what made the nail become magnetic? Think and answer me. Alright, the answer is a nail becomes magnetic because a magnet lines up the tiny particles inside the nail. Well done. Another question is, could copper or aluminium nail do the same? Think please. Bravo, your answer is correct. And the answer is copper or aluminium nails cannot do the same because they are not magnetic metals. Another question is, if the north pole of the magnet were touching the nail, what pole would the nail point be? Think again. Excellent. The answer is, if the north pole of the magnet touches the nail tip becomes a south pole. Another question, what is the process of temporary magnetization called? Good job. The process is called induced magnetism. My last question, what other materials can be temporarily magnetized? Brilliant. Your answer is correct. Iron, steel, nickel and cobalt can be temporarily magnetized. Now it's time for summarization and closure. A temporary magnet in a classroom becomes a gateway to scientific curiosity. It reminds learners that the world of matter hides intricate patterns that only reveal themselves when we probe carefully. and look beyond what our eyes can see. This may only happen if educators, teachers, try not to focus only on assessments and exam systems but engage students. On a critical reflection and through educational lens, this simple experiment is an effective pedagogical tool to introduce the temporary magnetism. It bridges observable phenomena, paper clips being lifted, when invisible physical mechanism like alignment of magnetic dipoles. It also encourages critical inquiry. For instance, comparing materials that can and cannot be magnetized promotes an understanding of material properties and atomic basis of magnetism. Please like, share, and subscribe our channel. You can leave your comments or questions below. These are our references. We will next meet you with some other exciting science experiment. Stay tuned to our channel. Thank you.